Residential energy conservation is a matter which has an impact on the daily lives of each of us. Recognizing the importance of this area, the Department of Energy, Office of Education, Business and Labor Affairs has supported a series of workshops conducted through the Oak Ridge Associated Universities. One of these residential energy conservation workshops was conducted at Oklahoma State University School of Technical Training at Okmulgee, Oklahoma. The following summary has been prepared to provide an overview of the highlights of this particular workshop.
To officially welcome you to our campus, it is now my privilege to introduce the Director of Oklahoma State Tech and Vice President of Oklahoma State University, Mr. Wayne W. Miller.
Thank you, Mr. Arterbury. Now, if we were really conserving energy, we wouldn't give you an unofficial and an official welcome both, would we? It's always interesting, the first person up in charge of the program, they just automatically say welcome. Then they introduce me to say welcome. Well, we're glad you're here, and it is a welcome officially to the first residential energy conservation workshop to be held on the Oklahoma State Tech campus.
The question is, could we particularly increase our production? And I'll leave that to the oil company to give you a little more information on it. And I touched slightly and just mentioned this least cost energy strategy, but I would like to refer back to it because it affects directly your question in that conserving domestic energy or conserving oil in effect would reduce the necessity for finding enough to overcome the shortfall. In fact, the Mellon Institute's analysis concludes that natural gas saved through more efficient use in commercial and residential sectors could therefore become available for expanded use in the industrial sector. In turn, increased use of gas by industry would therefore result in even lower oil imports. But now, you heard mention of cogeneration a while ago. In discussing this with one of their vice presidents, we talked about using a gas turbine. Okay, you run the gas in there, you burn it, it turns the turbine, you take the waste heat, you run it over to the boiler, you make your steam, you run the waste heat on over there and you make hot water. And by doing this, instead of looking at 30% efficiency or on straight power generation or maybe 50% on his boiler operation, now he's increased the efficiency way on up. So the actual use of base energy is going to be substantially reduced through cogeneration. This is the sort of thing, one of the things that is recommended by the Mellon Institute in their study.
Last year, our company made about $1 billion. $1 billion. Don't know what we're going to make this year, but this year we are spending $3 billion to look for oil and gas. Now, we've got to go to the money market to get the spare money. You know, the situation is obvious. We've got to make big bucks if we're going to do the big chore.
Heat is transferred by two modes. One is thermal radiation, the other is convection. Now, I don't want to insult any of you, but let me give you a little bit of background on these two modes. Convection heat transfer comes about because of air circulating and heat is carried by motion of the air from one place to the other. Thermal radiation is an electromagnetic effect, and heat is emitted in the form of waves from one surface and is absorbed by another surface. The intervening air does not absorb thermal radiation. It has been proven without a doubt that power fans generally do not conserve any energy. You know, the powered attic fans. Extensive field tests were conducted in the vicinity of Houston, Texas, on a number of houses, and that data was validated through also computer modeling and got the same results. Showed that more energy was used to run the fans generally than was saved. And then, of course, a very popular type of vent are these turbine vents. And early in my crusade, people were asking me a lot about turbine vents, and they are not particularly effective or as far as vents go, or do any more than any other kind of a vent. Generally speaking, it's going to be supplemental to a regular system. It'll have to have elaborate controls and piping. This is what a lot of people don't understand about a solar heating system on a house. I could have one, or Ed could have one, or Al, and mess with it all the time and keep it running. But if you were selling it to somebody and he wants a thermostatically controlled, no problem situation, it's got to have a very elaborate control system. And and so that's a consideration. Maybe this is a little bit out of date. I said here, consider as a last resort. I meant there, you want to consider all other alternatives such as gas heat pump and things like that before you go jumping into the situation. It's going to cost a lot. You better get ready for that. And it'll never pay for itself if you got natural gas. I think that's still true from when I made this slide 2 years ago. Now those are just general thoughts. There are a lot of applications for solar energy, and I'm not bad-mouthing solar energy. Just heating domestic hot water is a lot more attractive as a possibility. But generally speaking, solar, his time of it being real cost-effective is still coming. With the R7, the cooling cost is 4.7 cents per square foot. With the R19 is 1.7 cents per square foot. Now, the difference between those will then be the saving. And so here I've computed that. And it just is, I think it was a coincidence, it turned out to be the same number that we had for the heating, but I assure you it was just a coincidence. See, we have here 4.7 cents minus 1.7 times 1,800 square feet, divided by 100 to get it in dollars. So you see then the total saving was 54 for heating, 54 for cooling, or 108. Now, it was just a coincidence that those two come out the same. Now, if you look at it this way, if you consider that there's no escalation in the fuel cost or anything else, it would take about 3 1/3 years. So that makes it look a lot more feasible than it did before. 3 years is not a bad payout on anything.
You just put that down on paper and it boggles your mind that we throw away twice as much energy as we get in the form of electricity, and just think of all the electricity we use in this country. There's something wrong with that. Okay, so you can see that's probably not a good deal. And I'll say this right now, our company in Stillwater will not install an electric furnace. If a guy comes in and wants an electric furnace, I say, go see my competitors. And then in a couple of years, when you can't afford your electric bill anymore, come around and I'll make more money replacing it than he made installing it in the first place. And it's the truth. And I have some very good friends with ONG, but the fact is you can take electricity and beat the pants off of it. I'll come down to a gas furnace and we show an efficiency of 60%. And on every furnace label that Carrier or Fetters or Lennox or anyone else builds, they show an efficiency of 80%. 100,000 BTU furnace, that's input, and you look on the little tag and it says output 80,000. Well, that's in a laboratory running 100% of the time with an engineered vent system on it, exactly the right amount of combustion air and so forth. The fact is, in a house, when I go out, and we're good, you know, but let me tell you, when you go out and put it in the house, first of all, you have cycle. Because you got to put the furnace in there that'll carry the house at whatever the lowest temperature is going to be outside in the wintertime. We designed for 0. So it only hits 0 here about 3 hours a year. Maybe 5, I don't remember the exact number, but it's not very much. Well, any other time, that furnace is oversized. And of course, our average winter temperature here is around 40 degrees. So you can see how much oversized it is. With the heat pump, and by the way, this is not perpetual motion. This machine simply goes somewhere and is able to capture heat from a lower temperature than you want to use it and pump it up to a higher temperature. That's all a heat pump is. That's all any refrigeration cycle is. It's simply a machine that will pump heat from a low temperature to a high temperature, just like a well or a pump in a well will pump water from a low spot to a high spot. It defies gravity. Well, this defies the laws of thermodynamics the same way. By adding some power, you can pump that heat uphill. Okay, if we can get to somewhere along here, actually it'd be about 3.3 or something, would get this graph down to exactly what that is. If we can do that, then we're getting 100% efficiency out of our source fuel. We use this much to generate the electricity, but we came back and for every one of these that we used, we got 2 or 3 more free. Out of the ground, out of the air, wherever we want to get it. Out of wastewater, out of a pond. There's a million places that there's nice heat for a heat pump. Anyway, if we can do that, then we can get over into these areas, and actually you can make it more than 100% efficient. Because you're using your energy to move heat, not to create heat. And I might just mention right now that with the refrigerants that we use today in typical air conditioning and heat pump systems, that temperature will be 180, 190, maybe 200 degrees when it comes right out of that compressor. And you have to cool it down quite a ways. In fact, you have to cool that down to about 120 degrees or 110 degrees, somewhere like that, before it will start turning into a liquid. And it's that difference that we call superheat. From the temperature it is down to where you have to cool it before it starts condensing into a liquid. Now, one of the things we do, I'll just kind of mention this in passing, one of the things we do is right here where that hot gas is coming off the compressor, there are several devices on the market now called desuperheaters or hot water preheaters. Carrier's trade name is Hot Shop. There's ECU units. Heat Stick is the one you have a piece of literature on there in the handouts. But anyway, what we do is we take that very hot gas and somehow put it in contact with your domestic hot water, or your domestic water, so we can make hot water out of it. And the little heat stick there that we show you is the simplest one we've seen. That's simply a rod that screws down in the hot water tank, and this hot gas comes over, goes down through that stick in the hot water tank, and then back, and then goes on its way. And we can sit there and hold a hot water tank at 140 or 50 degrees real easy without any outside energy going to it. Now in the summertime, that's free because that's heat you're removing from the house and you have to get rid of all of it anyway.
If any of you want to play golf this afternoon or later, if we don't get rained out, we can arrange it for you. We're going to call out to the country club and work it out to where you can sign up on Steve Corley's card.
This is the basis of the whole horizontal earth coil system. And again, I want to point out right here that what we've done is we have taken water source heat pumps, or we have taken air-to-air heat pumps, and we have adapted those to water source machines. And the earth is a gigantic flywheel. As you go deeper into the earth, beyond the 4-foot level, this curve will have less and less amplitude until, like Carl said, after you get 10, 15 feet in the ground, it's level. It's constant. As a matter of fact, if you integrated this and averaged it all out, the average temperature should be, in our area, should be 62 degrees. At that time, we had developed kind of a design for the earth coil. We wanted to use a 4-inch, 160-pound test PVC pipe, and we decided that we would lay it in the same 2-foot wide trench, 4 feet deep, and we would just simply take these 2 pipes out to the septic lateral field and then bury them beneath this 3-pronged septic lateral field. Next, we get a schematic diagram. The dashed lines are the septic lines and boxes. The solid lines are the earth coil lines. Cross-section showing the earth coil lines and the septic line. And in this total system, going all the way back to the house, I think we had 840 feet of 4-inch PVC, and approximately 600 feet of it is out here in these lateral lines. And I have a couple of inspection ports out there where I can peer down in there And it is very wet down here. It is, in certain areas, there's a great deal of liquid in here, and it's very wet. So I think we can confidently say that whatever heat transfer rates we're getting, it is between PVC plastic pipe and very wet sand-packed soil. And then once you get out away from the sand fill, we have that very familiar old Oklahoma red clay. I think we can move on. Now, the reason that we buried those things under the septic field is that in our early research, we found that the coefficient of heat transfer varied by a factor of about 10 to 1 between dry soil and wet soil. As a matter of fact, very dry sand is a good insulator. In the equipment distribution business, we have to work with dealers to try to get them up to speed on how to install water source heat pumps. And then we have to work with drillers on how to drill these, what we now kind of lovingly call geothermal wells. To go back over the construction of the well, notice it has a cap on both ends. And we try to bury them below the frost line, and we try to get these lines run in well below the frost line, and preferably the lines spread apart in the trench so there won't be any conduction, between lines. Here you see the two pitless adapters. Here's the internal adapter piece with the discharge tube hanging on it. Of course, this is greatly foreshortened in our drawing here. And in our area, around here in Oklahoma, we've been getting by with about 100 feet per ton. And reduced into dollars, that's about $650 or $700 per ton. The actual equipment room installations that we've been making are about the same in cost as regular air-to-air systems. So these systems have a premium price associated with them, and that largely can be isolated to the cost of the well itself. The question was, can you tell if there's any storage factor? And I'm going to give you in one sentence what the United States Department of Energy paid $160,000 to find out. In terms of time, the time constant associated with the earth coupling, 1 or 2 days is forever. You could run a heat pump non-stop, suck heat out of the ground, check the temperature of the well bore and the surrounding area. You could run it for 2 months solid, turn it off for 12 or 24 hours, and you can't ever tell anything ever happened. The time constant is 1 or 2 days. 1 or 2 days is forever. Okay, the heat transfer rate, another important thing, and this is based on linear feet of well bore. This is the other, they paid a third of that $160,000 to find this out. The heat transfer rate is not a simple thing. It depends, since the time constant is very short, the heat transfer rate depends on cycle time. If the machine is run non-stop for 30 days, the heat transfer rate is lower than it is if the machine is running 50% of the time and cycling. Savvy? In other words, say you were heating the house and you're chilling the well bore. If you run constantly for 30 days, that constant will be about 2.5 BTU per linear foot of well bore per degree Fahrenheit delta T average from well bore to far field per hour. If you're in a high cycle situation, it may be 3 or 4. And in here lately, Carl and I have a privileged position. We get all the data from the research program at OSU before the Department of Energy does. So I'm telling you things that they don't know yet. We have a research well there where it's not a PVC well, it's a steel casing with a closed loop in it. Insulated loop down, uninsulated loop up. It's a copper and plastic loop. It's a sealed heat pump system, but it's an open well, research well. And the performance number on that is 5 after extended runtime. So there's a lot of ways to do these wells, and we are not completely certain that the way we're doing them is the best way. We're doing them the best way that we knew how when we did them. Let's see, there's another important thing. The rest of the $160,000 they paid to find out what is forever in distance. The answer to that's a couple of feet. 2 feet away from the well bore, you can pump on it for 2 months and you can't tell anything happened. 1 or 2 days and a couple of feet, and 2.5 or 3. They got a hell of a bargain for that $160,000.
We term this the best kept secret in the solar business, is tax credits are allowable for solar applications. This slide was recently received as late as this morning when I was in the office going through the mail. I opened this one and said, here's your latest tax slide. So it's just convenient that it worked out. But this is the way it presents itself now. This was a part of the windfall profits tax that went through. Our oil and gas interest is going to suffer a little bit, but we're smiling out of one side and frowning out of the other, because this gives us the ability to figure 40% tax credit now, up to a maximum of $10,000 for the cost of an installed residential hot water and space heating system from the federal level. Now, let me point this out to you. Yesterday, the Oklahoma Senate was to meet and discuss the possibility or probability of a new solar tax increase from the state level. It presently is 25%. So if we can take our 25% into 40%, we're talking about a 65% cost off the cost of the solar energy application in this area. The Senate was to consider yesterday the probability of raising that 25% up to 55%. If and when it becomes law, the residents in Oklahoma will be looking at not only 40% from the federal level, but 55% from the state level as well. What does that say? That says 95% of the cost of the solar energy application in Oklahoma can be written off in tax credits. A solar hot water system for an average family of 4, that would be 2 collectors. That would be a heat exchanging module, which I'm sorry, I'm afraid we're not going to get into because of time, but please stop by and we'll look at it after the class. And an 80-gallon storage tank would cost you in the neighborhood of $2,200 for the equipment. Now, that's not installation, that's just equipment. Okay, taxes, it's going to vary depending on where you live, what your sales tax is, 2 to 4, 5% would be in addition to that, and installation would be in addition to that. A ballpark figure from installation would be anywhere from $600 to $1,000, depending upon the length of copper runs and the amount of insulation required. Any other questions?
Anything on payback on that?
I'd rather you not ask me about payback. I'd rather you ask utility companies, because people would tend to think that maybe I'm biased, but I'll give you my heartfelt opinion on the data that we've worked up. Versus electricity, we can sell you a system just about like I described for about that money that I described and show you a payback versus kilowatt hours consumed. And you'll realize that money that you spent out, if you can take your tax credits, are allowable in a 4.5 to 5 year period. Now, we're assuming an annual inflation rate of about 10% per annum, which when we were figuring that was a little high, but now it appears a little underestimating it. Now, versus natural gas, we're projecting that figure on out to around 7 to 7.5 years.
We occupied in November. We're on the East Central Rural Electric Cooperative utility rates. And unless I had all the charts here, and we do have daily logs, it doesn't mean a heck of a lot, but I can tell you with a family of 4, 2 teenagers, junior and senior, who use gobs and gobs of hot water, and I don't have active solar, Ken, as you know, at this time. But my highest utility bill on 2,250 square feet, all electric, was $78. I'm pretty happy with that. We've got 185 square feet of Pella on the south, and passive solar works.
To start it off with, we'll go through the original concept, the Arkansas story. To make a presentation on that, we have with us this morning Bill Byers, the conservationist from the Public Service Company.
We have the Public Service Company, what we call our Energy Efficient Electric Program. And it is basically the Arkansas home. Now, as you can see, what we're recommending, ceilings, we're not specifying just how you do it, but in a ceiling, we'd like to see an R38 or an R30 minimum. Walls are 19, wood floors are 13, and slab floors 7. Now you can get that in different ways. You can go batch, you can blow it, you can put the polyurethane or the styrofoam slabs around the slab floor, under the slab floor. As we'll go through, I'll show you how. But these are things that need to be looked at real close. As you start building the house, you need to do a few other things in, such as sill sealer. You're losing energy, you're losing dollars. So the tighter you can make the home, the more you can keep that conditioned air in that space, whether it's heated or cooled, it's conditioned air, then less dollars. And that's what everybody's after. They want to be able to live in a house that they can afford. It's not just the house payments anymore. It's what the utility bills cost.
This is the slab for the house that is least nearest completion that we'll be looking at this afternoon. We are building a 7-foot 3-inch ceiling. And if you figure that up, we're cutting about 10% of the airspace out of the house. And we're just having a lot of success with this type of installation. Here again, we talked about the 7-foot ceiling. I said 7.3. It works out. I tell you what we do. We buy a 14-foot material and we cut 2 7-foot studs, and you get your plates on it. It comes out 7.3, and it works just pretty good.
This is just a general picture showing everybody goes out and finds a very, very attractive site and picks a spot, and then they enhance it with a bulldozer. The question is, what about concrete block? Well, I have a prejudiced viewpoint because I was formerly a bricklayer, but I believe that the bottom dollar in these is with concrete block. Those sulfur houses were planned to be concrete block, but they couldn't get any masons out there that far out. The subsidy was too high, and they happened to have a local man that wasn't afraid of forming, so they went the other route. I feel like, well, you know, you can get a block wall for $2 or $2.50 a square foot, and you're paid $5.50 a square foot for a poured wall 2 years ago. The difference will more than fill that with concrete and put bars in it. And also, I would think, in most cases, you would be able to get, you wouldn't care about workmanship on that wall. As long as those block got laid up anyway at all with a perfect bond so you could put a bar down every hole. You're going to have to waterproof it anyway, and maybe you'd want to finish the inside. You would at least have the option of finishing one side with block. Or if you're going to cover it up, it doesn't matter either.
You would fill every cell?
I would. I'd pour it full. I'd just use the block as a form. My idea of a good way to build, and I'm going to have to do it myself to prove it, I guess, is use 12-inch block and let your dowels come out of your footing about 2 feet. Keep perfect bond. Don't let your bond shift one bit. In other words, keep your layout all modular 8 inches so that you go on up. Set your steel joists on the wall, deck it, and then fill in between the joist seats with a course of brick, and put your curb on the outside with a half-high block or whatever block it's going to take, and pour the whole thing at once, using grout or pea gravel concrete to fill the walls. When they're filled, then change over to hard rock concrete. I know that's got to be the way to do it.
Where did you come from, Mr. Thompson?
I'm mainly interested in geothermal systems, and I think we're going to cover those. That's basically what I'm interested in.
Okay. Why didn't you go to Sonoma, California?
I don't know what Sonoma, California is.
Biggest geothermal fields in the country. How did you find out about this program here?
They have some geothermal systems in still water. They had a seminar that last month, but I was in school and I couldn't attend, so I thought this would set some best.
Okay. How were you recruited to this program? How did you find out about this program?
My dean gave me a letter.
The dean gave you a letter. How about you? How did you find out? We got a mailing. Mailing brochure? Okay.
Same way.
Same way?
Yes.
Okay.